Hi, my name is Yash Kumar. Today I will be presenting you a session on dynamic programming for IEEE CSVIT. So let's look into this. So our prerequisites should be you should know recursion like in merge, sort and all. So what is dynamic programming? So in dynamic programming, we solve problem by combining the solutions to its subproblems. Now, what are subproblems? Subproblems are like the same instances of problems, but it's for like the same. It's the same thing, but for smaller problems. Okay, so we will see it further. So it is a technique in computer programming that helps to efficiently solve a class of problems that have overlapping subproblems and optimal substructure properties. So we will look at. So first we will see this by an example, which is rod cutting problem. So we are given a rod of length n and array pieces of length n, denoting the cost of pieces of the rod of length 1 to n. Find the maximum amount that can be made if the rod is cut up optimally. So this is our problem in hand. So let's look into one example. Like if we have n is equal to 8 and our prices are given to be 1, 3, 4, 5, 7, 9, 10, 11. Okay, so we can just, for example, this is our rod, okay. Uh, its length is 8. Now our task in hand is to cut it in smaller pieces, and for each smaller piece, for a given length, we have some kind of value associated with it. Let it would be the cost of that rod. So we are given cost for rod of different lengths. Okay, like here, like if we have a piece of size 1, then we will get 1 rupee. If we have piece of size 2, then we will get 3 rupee. Okay, so one way of cutting this rod is we may cut it like 2, 2 and 4. Okay, so this is one way to cut our rod. Okay, so let's calculate how much we got from our this solution, meaning how much we can we get from this specific solution that we got. Like so, the cost for the length 2 rod is 2. No, it's 3. I'm sorry. So the total cost here would be 3 plus 3 plus 5. It would be like 3 plus 3 plus 5. That would come out to be 8 plus 5, 13. Okay, understood why? Because the amount of money we will get from this piece is 3, and from this piece is 3, and from this piece is 4. Okay, so the total amount we can get by this way is 13, but this may not be the best way to cut this rod. Okay, we will see it further in the next slide. So the best way to cut is 2 and 6. Okay, so the best way to cut our rod is to cut our rod into two pieces, one having the length 2 and one having length 6. So that will give us total cost 3 plus 9 is equal to 12. Okay, so this is what our problem is stating. So how do we solve this? Uh, basic thing to understand while solving is the optimal substructure property. So suppose we have a rod, okay, and we have decided our first move that if we have a rod of length A, then we will cut it into two pieces of length B and length C. So the optimal substructure property says that after we have made our first move, then yeah, after we have like after we have made our first move, then the resulting rods which we are getting, in this case rod B and rod C, should also be cut optimally. Uh, so this is what I'm trying to say is, suppose we have a rod and in the optimal solution we cut it somewhere here. I don't know it where, but I'm just assuming it that it is here. So if I know that, if I suppose that this is here, then I know one thing for sure, that the optimal solution will be the summation of the optimal solution for this part and the optimal solution for this part. Okay, I think this is understood by common sense. Suppose its length is A and its length is B and C. So this is optimal substructure property. The solution to this larger rod lies in the solutions to these smaller rods. Okay, this is the optimal substructure property. Okay, so the way we solve this is, first we take a rod. Okay, suppose our function name here is, I'll show you the code. This is our nice approach of doing it. Suppose our function name is maximum profit. Okay, so we will firstly, it takes two things as a input: a vector of prices which is just an array, and n which is the length of rod. Okay, so in our solution what we are doing is that, in our code what we are doing is that, suppose this is our rod, then we are iterating over the first cut we make. Okay, we'll check for all the first cuts. Okay, suppose this is the first cut from, okay, suppose this is the first cut from right. Okay, this is the first cut, so we won't cut this part any further and we can cut this part further more. So we can say that if this is our first cut, then the solution would be the cost of this rod plus the optimal solution for this entire rod. Okay, one thing is should be clear that we won't cut it further. So we can iterate over this first cut from n is equal to 1 to n is equal to n. Let me show it. N is equal to 1 to dot n. So in the case of n, we won't be making no cuts. Okay, so this is our code. I will explain you. So it takes I is where we make our first cut. It goes from 1 to n. And in case of any I, the profit would be the price of I minus 1, that is uh, this part, this is the price I minus 1. If this is I minus 1 because we are using a zero index array. So this is just price I minus 1. Okay, sorry for my bad handwriting. I'm just showing you. And this part is in the code. This part is maximum profit prices and okay. And what our code does is it returns the maximum profit. So I think there might be a little bit error in this code. Uh, let me just check from its source. I think. Uh, yeah, this is what I was talking about. I took my code from this website. I'll just copy it and show you in this thing. Let me open it. This is hard. I'll just explain you the code. Okay, so we are iterating for the first cut from I is equal to 1 to n, and our profit for I would be the price of the ith piece plus maximum profit of prices and n minus I. This is what I was talking about. Uh, so this is our first cut. First cut. So this is prices of I minus 1, and this is max profit of the rod of length n minus I. Okay. So for each I, we would iterate and find the maximum among those I. Okay. So this is how we will do it. So basically what it does it checks for all the possible ways of partitioning the rod. So in this case, that would be 2 to the power n minus 1, which is exponential. So like that would be very bad for our case because suppose if we have n is equal to 30 or 40, then or 50 maybe, then then it is far beyond the reach of our normal computers to compute it. For example, your desktop computers and all. So this is very bad. So this is not a proper solution to this. Okay, this is not a proper solution. Means time complexity wise it's not good. So now we'll try to optimize it. Now here comes the second property that we are talking about. One was the optimal substructure that we already looked upon, and the other is overlapping subproblems. Suppose we are trying to solve for a rod of length 4. Then just look here. We will call that function for 3, for 2, for 1, for 0. So here this is we are calling this recursively for the rod of length n minus I. Okay, this is a recursive function. If you understand recurrences and recursion, you would get this. So For solving for a rod of length n, we will be calling for 4 we will be calling 3210, and for 3 we will calling 210, for 2 we will calling 100. So one thing you should notice here that we are calling, for example, let's say 2 again and again, and we are again computing it, which is not at all required, because if we compute it for the first time we can just store it. So this would be our idea of dynamic programming here. So same instances of some problems which I just said are computed again and again in our code. These are examples when subproblems overlap. In this case, for example, 2 is overlapping in these two recursive calls. 1 is overlapping in these 3 or 4 recursive calls. So this is it. This is how we'll try to solve this problem. So how do we store it? We can easily store it by using a technique called memoization. So this dynamic programming method works as follows. Having observed that a naive recursive solution is inefficient because it solves the same subproblems repeatedly, we arrange for each subproblem to be solved only once, saving its solutions, what I just said. So we will just change our recursive code. So I'll just copy it because just look at it here. Let's look at our code here. So the function is what can you observe the difference between our original function and this function. This was our original function, okay. What are the changes you can observe? Okay, I'll just copy it there. So it's easy for us to get what is the difference between those two. So this is our new function. I'll just add a line here. This is our new function and this was our old function. So what we are doing is we are actually initializing a new array and initially setting all of its initial values to -1. Okay, so our technique works like this. Whenever we call our function, we will check if we have the solution to that stored in our array. If it is not stored, then its value would be default, that is -1. But if it is not -1, means that we have already solved this problem and we will directly use that value. Okay, so here it goes. If it is not 1, return directly that value. Okay, but if it is -1, then just compute it like before and then just store it in our array. So how does it modify our time complexity? We will see. There are n subproblems. For the rod of length n, we will have n is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4, and so on. So there are only n subproblems, and each will take a linear time because of a for loop. Okay. Hence, the overall time complexity will reduce to n square. So this is a very good jump. Okay. So 2 to the power n to n square. This is a very good jump. Suppose for n is equal to 100, we'll do like millions and billions of steps here. Okay, I don't think that any supercomputer can also do it. But here we will only take like 10,000 steps. I think that our computer can do it within a second, even 100 milliseconds, I think. So this is the gap we are creating here. So this was all about dynamic programming, memorization based approach. So I think there are few other things that we may talk about, but I think that would be too much for one session. Uh, Let me just draw these. So there are other types of problems like 0 1 knapsack problem, okay, and longest common subsequence problems. So those are the examples of 2D dynamic programming in which our function will take two parameters as like two parameters and we will store it in a 2D array. So basically that thing is also same. I'll just give you a little bit of idea about the 0 1 knapsack problem here. So in 0 1 knapsack problem, we will be given an array of costs and weights. Okay. Each item will have a cost of Ci. I'm just giving you a basic idea, and each item will have a weight Wi. So, and we will have a maximum weight W, and we want to maximize our cost. So one basic way would be to select all the subsets of our items. That would take exponential time. But there is another clever way, like we can just store uh, for like there is a 2D way of solving that. Like we can make our parameters as I, which is the item we are on, okay, and W, which is the total amount of weight we have. So that way we can reduce it to something like and W. Okay, I'm just giving you a very basic idea. You can look into that because my lecture wasn't supposed to cover this. I'm just giving you a basic idea. So this is it, guys. This is all I wanted to show you about dynamic programming. Thanks.